Okay, so now let's use what we learned about ionic and covalent bonds to go through and look at some bonds between different atoms and decide if they are actually ionic or covalent, and if they are covalent, are they polar covalent or nonpolar covalent. So in other words, do they transfer electrons, do they share electrons equally, or do they unequally share electrons? So we'll go through these one at a time, kind of talk through the steps. So if I have a bond between hydrogen and oxygen, first I need to check the periodic table, the electronegativity table, and find the electronegativities. So you'll find they are 2.1 and 3.5. So the difference in those numbers, the largest minus the smallest, is 1.4. So remember that 1.4 falls into the category of polar covalent. Okay. So they unequally share electrons. So then it asks us, let me back up, you can skip the percent ionic, percent covalent character. That's not something I'm worried about. That's not an important concept. You need to be aware that it exists, but you don't need to be able to predict the percentages of each type, so don't worry about that column. So then, for dipole arrows, that's kind of a new concept. Let's talk about what we already learned how to do for polar covalent bonds. So if we have a hydrogen bonded to an oxygen, I know they're unequally sharing these electrons. So I know one of these atoms is going to more greatly attract an electron. So it is the one with the greater electronegativity, so oxygen. So oxygen is slightly negative, hydrogen is slightly positive. So you learned how to do that already. The dipole arrow is just another way of showing that. So this is what we call a dipole arrow. So a dipole arrow shows the direction the electrons are being pulled. So the oxygen pulls the electrons more towards itself than does the hydrogen. So the positive tail goes by the slightly positive atom, and the electron points in the arrow points in the direction the electrons are being pulled. Okay, so when asked for the dipole arrow, you can just draw it like this, or if you wanted to label slightly negative and slightly positive, that's the exact same concept. So let's look at hydrogen and nitrogen. So we have 2.1 and 3.0. So when you do the electronegativity difference, you find it is 0.9. So 0.9 falls into the category of polar covalent. Okay, so I need to draw out the dipole arrow. So hydrogen bonded to nitrogen. The electrons are being pulled towards the nitrogen because nitrogen is more electronegative. So nitrogen has the slightly negative charge, hydrogen has the slightly positive charge. Okay? So I'll leave some of these for you to do on your own. Let's go ahead and jump down to the bromine and chlorine bond. So for bromine and chlorine, you have 2.8 and 3.0. So when you do the subtraction there, you get 0.2. So for 0.2, you have nonpolar covalent. Okay. So if you have nonpolar covalent, you have equal sharing of electrons. So when bromine and chlorine bond together, the electrons are shared equally. So I don't need to show the dipole arrow here. You only show dipole arrows for polar covalent. So you can make a note only for polar covalent. That's when the electrons are being unequally shared. So for here, you're done there. So let's look at the examples of hydrogen and sulfur and hydrogen and carbon now. So each of these you'll see have electronegativities of 2.1 and 2.5. So when you do the subtraction, you get 0.4. Okay, so that kind of falls between the rules for polar covalent and nonpolar covalent. So I said the rules weren't really hard and fast and set in stone, but typically we do want to consider 0.4 as being nonpolar, simply because the carbon-hydrogen bond is so common in organic chemistry that we'll discuss later, and we assume that is a nonpolar covalent bond. So you can go back and edit your notes previously if you want to. If you want to say that the electronegativity difference from 0 to 0.4 with 0.4 included is nonpolar, that's perfectly okay. But for the sake of this class, we'll label these as nonpolar covalent. then there's no need to draw the dipole arrows if it is nonpolar covalent. So for chlorine and chlorine, do we even need to look up the electronegativity values here? You should say no, we don't, because they're going to be the same number. So the difference is going to be 0, so they're going to be nonpolar. Okay? So a bond between two of the same nonmetals is always going to be nonpolar because the electronegativity difference is 0. So then let's look down at potassium and bromine. So potassium and bromine have electronegativities of 0.8 and 2.8. Okay? So when you subtract it, you get a difference of 2.0. Okay? So you would call this an ionic bond. Okay? Because the electronegativity difference is greater than 1.8. But did I even need to go through this process? No, I didn't. Because I can recognize potassium is a metal, bromine is a nonmetal. It's automatically ionic. So for the next one, sodium and oxygen, I can skip these steps. I have a metal and a nonmetal. It is automatically ionic. Okay? So when it is ionic, I do not need to show a dipole arrow because there is no dipole arrow. The atoms have a permanent charge. Okay, so potassium would have a permanent positive charge, sodium a permanent positive charge, oxygen permanent negative, bromine permanent negative there. Okay, so if you go through the steps, that's fine, but you should recognize initially you have a metal and a nonmetal, you have an ionic bond. So just kind of in review, what we have going on so far, a bond between a metal and a nonmetal, or between two nonmetals, or a nonmetal and a nonmetal and a metalloid that have an electronegativity difference greater than 1.8 are ionic bonds. Okay, so they form ionic compounds. Compounds with an ionic bond we call ionic compounds, and they completely transfer electrons. So bonds between two atoms that have very similar electronegativities we call nonpolar covalent bonds. Okay, so two of the same nonmetals are nonmetals with very similar electronegativities we call nonpolar covalent bonds, so equal sharing of electrons. Then we have bonds between nonmetals with electronegativity differences greater than 0.4 but less than 1.8. We call them polar covalent bonds. So polar covalent bonds unequally share electrons and result in dipoles being formed. So we have a positive dipole, a slightly positive charge, and a negative dipole, a slightly negative charge.